For this lesson, we'll be focusing on fiber optic communications. So what's so special about it? Well, fiber optics encompasses the method of transmitting information via light instead of electronic pulses. And over the past couple decades, fiber optic systems has actually undergone a major development. In fact, it has a major impact on our commercial and military organizations, and as far as replacing our copper counterpart, in other words, your Cat5 cable. In fact, it's made a major impact on over long distances, such as over across the Atlantic. As you see in the illustration below, provided by the New York Times, you could see where these lines are actually fiber optic cables running under the water just to actually provide some communications. So what makes fiber optics so special? Well, there's a list of advantages. One, it has extremely wide bandwidth. Second, it has immunity to electrostatic interference. Since it uses light as its transmitting source, it's basically immune to any type of crosstalk or any type of interference with cables next to each other. That being said, it's also lightweight and small. Since fiber uses glass to actually transmit its light, glass is very thin and very light compared to copper. Low cost. Well, like I said, since it's made of glass, it's actually using sand to actually create these fiber cables instead of copper. Copper is actually relatively expensive compared to glass. It has minimum safety hazard. Since it's not carrying any voltage, it's carrying light, it has less safety hazards. There's still hazards, but it's less. You don't have 480 volts or high voltage going down these lines. It's environmentally resistant. Again, since it's made of glass and it has a jacket, it can actually be stored underwater or actually used in various harsh environments and actually resist any of the elements, the weather elements. And most importantly, fiber has a very high security. Since it's very hard to influence this fiber without direct connecting or actually influencing the actual cable, you have a very high security system with fiber optics. So now that we put fiber optics on the pedestal, now we can start and get to the weeds of how it works. The first thing we're going to go over is the optical spectrum. This is defined as the electromagnetic radiation with wavelengths in the range of 10 nanometers to 1,000 micrometers. And this translates to 300 gigahertz to 3,000 terahertz. So if you'll see on the illustration, you'll see the optical spectrum or the electromagnetic spectrum, and it goes from gamma rays all the way to radio waves. And right in the middle is our optical spectrum. This is the area or the wavelengths in which we transmit within fiber optic communications. Now, if you noticed, I actually use the term nanometers and micrometers because in fiber optic industry, you'll see on the data sheets, they use nanometers instead of frequency, which is in hertz. Because anytime you hear radio frequency or radio transmissions, you think of hertz. When fiber optics, they use meters. And it's very simple to equate that in frequency. We have a wavelength equation at the bottom, which is your speed of light over your frequency. And you can swap that around if you want to find your frequency using your wavelength. So let's go over the construction of a fiber optic cable. It's usually broken up into three parts: the core, the cladding, and the protective jacket. Well, the core is the portion of the fiber strain that carries the light. It's the very center. This is typically made of glass. However, sometimes it can be made of plastic depending on the manufacturer. And the size of it ranges from 8 micrometers to 200 micrometers. Now, to give you an idea how small or how thin that is, the human hair is 100 micrometers. So think about that. The core is substantially smaller compared to a human hair. Next is your cladding. This surrounds the core of your optical waveguide, and this is actually a plastic coating to protect your core. And it's usually about 125 to 240 micrometers. Last is your protective jacket. This covers the cable as a whole and isolates your cladding and your core from the outside elements. And it's typically made of PVC or polyurethane. Now, anytime you deal with light in two different medias, the term refraction comes in. And the same concept applies to fiber optics because we have a core, which is typically made of glass, and then we have a cladding, which is typically made of plastic. And those are two different medias. So you have your core index and your cladding index. Now, if you remember the old physics books, when you see refraction, you have Snell's law. And that tells you the actual reflection or refraction based on these medias. Now, same concept applies to fiber optics because in fiber optics, light does not actually move continuously through or a straight line through a fiber optic cable. It actually reflects or bounces down these fiber lines. So in these data sheets, you'll see a term called numeric aperture. And this is actually a manufacturer specification that indicates the ability to accept light and show how much light can be off axis and still be propagated. Now, numeric aperture is usually a decimal point, usually less than 1. However, you can also find the angle using the equations below. Now, in the fiber optic world, there's 3 different types. There's single mode step, multi-mode step, and then multi-mode grade index. So let's go over the first one, single mode step, also known as mono mode. Well, it's basically a one straight shot, and it's usually down a very small course, 7 to 10 micrometers. And the straight shot is ideal for very long distances, thousands of miles. The next type we have is our multi-mode step. It's very short distance, less than 2 kilometers, and it's rarely used for telecommunications. It's usually due to the amount of dissipation and the minimum bandwidth capability. It's very sporadic of how it transmits lights through its core. And the core for this one is usually 50 to 100 micrometers. And then the last type we have is very common. It's our multi-mode grade index. Again, this is very common, used in various networks, server rooms. It's something you'll typically see in a lot of industrial and commercial use. Now, why do we use the multi-mode more than the single mode? Well, single mode, even though they're actually very expensive fiber optic cables, it's actually the transmission or the transceivers that actually can kill you on the cost. Because single mode step, you have a very small core and you're only shooting one shot down it and it's like a laser. Well, that requires very high precision. Well, anytime you have something that's high power, high precision, and small, it gets very expensive. So typically what you'll see is the multi-mode grade index, because it actually has very good transmission capabilities, as well as it's very inexpensive compared to its single mode counterpart. Now, if you notice in the previous slide, I used the term dissipation. Well, the reason being is in fiber optics, there's 2 common distance limiting parameters. It's attenuation and dissipation. Well, first we'll go over attenuation. It's the loss of power as the signal propagates through a fiber optic line. So the longer the fiber optic cable, the more attenuation there is. And on your data sheets, this is typically expressed as decibels per kilometer. Now, if you notice, attenuation refers to the loss of power, because in fiber optics, we use loss of power versus gain. You'll hear attenuation versus gain. Next, there's dissipation. Dissipation refers to the broadening of light pulses as it propagates through a fiber strain. Basically, the pulse is spread out in time with longer rise and fall times, which increases pulse width. So if you see in the illustration below, your source is sending a pulse of 1, 0, 1. Well, since your actual pulse widths are increasing, your receiver is seeing 1, 1, 1 because it didn't fully dissipate yet. So that's your 2 distance limiting parameters, attenuation and dissipation. Now the last thing we want to go over is system design. For system design, you want to look at system gain. It's the difference in decibels between the transmitting source and the receiver sensitivity. So this is where you'll see the term link budget come in, because an ideal system would equal, preferably exceed, your link power budget. This budget includes your source power, your receiver sensitivity, coupling losses, your length attenuation, aging, and any other loss entity. So if you look in the illustration below, you have a transmitter sending light. Unfortunately, this light is going through a long cable, that's where attenuation comes in. It goes through splices. Well, anytime you mate or actually splice 2 fiber optic cables together, there's going to be some degree of loss. And then it goes out to the other end to the receiver, which has a sensitivity. It's actually expecting a little bit of loss. And then you have your output, which matches your input. And we're going to go over an example of link power budget in the example problems. All right, for our first example, we're going to start off with an easy one. For this one, when checking a spool of fiber optic cable, the source power is 3 milliwatts, and it decreases to 10 microwatts after traveling the entire length of the cable. Based on its data sheet, the attenuation for this fiber optic line is 2 decibels per kilometer. So we want to determine the length of the line and the signal noise ratio. All right, so we have a few things we need to figure out. First thing we should do is take our power and convert it to decibels. Now, if you remember our signal noise ratio video, the way to convert power to decibels would be to use decibel milliwatts. We're going to say decibel milliwatts equals 10 log, and then it's going to be power over, and we're going to do it in reference to 1 milliwatt, which is 1 times 10 to the negative 3 watts. Anytime you're converting power to decimals, it's best to do it in reference to something. Sometimes it's noise, sometimes it could be milliwatts. for this case, we're going to do milliwatts. So we're going to get decibel milliwatts. So for the first one, we're going to say decibel milliwatts equals 10 log, and then we have power of 3 milliwatts, and this is over 1 times negative 3 watts. Okay. And obviously 3 milliwatts over 1 milliwatt is 10 log 3. So in other words, this is going to be 10 log 3. And that's going to give us a simple plug and chug answer of 4.77 decibels. So that right there is actually our source power. Now we want to determine what it decreases to. So we're going to do the same song, different verse. We're going to say decibel milliwatts equals 10 log, and this one's going to be 10 microwatts, so it's 10 microwatts over 1 milliwatt. So we can just plug and chug that in that calculator, and that's going to give us an answer of negative 20 decibels. So that means our actual receiving end is going to be negative 20 decibels. So we start off with 4.77 decimals, and this is going to be milliwatts, and we end with negative 20 decibel milliwatts. All right, I'll tell you what, I'm going to move this up here so it gives me a little room. So we're starting off with 4.77 decibel milliwatts, and we're going to end on our receiving end at negative 20 decibel milliwatts. All right, now let me go ahead and erase this. So the first thing I'm going to do is I'm actually going to go with the easy one first. I'm actually going to determine my signal-noise ratio. Well, the way you do that is for the signal-noise ratio, you want to determine the entire length from your power all the way to your receiver. So in other words, if you want to look at this at a band, I'm going to cheat a little bit. There's a straight line right there. So in the center is 0. And then we're going to go 5, 10, 15, 20. Then negative 5, 10, 15, 20. And I'll tell you what, I'll put them in here. That way it's easy to follow along. And 5, 10, 15, 20. All right. So we started with 4.77 decimal milliwatts. So it's going to be approximately right there. And that's 4.77 decibels. And then at the receiving end, it's actually traveling from there all the way down to right here. So right here, we have our receiving number of negative 20 decibel milliwatts. So where is it traveling from? It's traveling from 4.77 all the way to negative 20. So that means you have 4.77, and that's going to be minus your actual receiver, which in this case is negative 20 decibels. And I don't think we need a calculator for this one. The two negatives cancel out, and that's going to be 24.77 decibel milliwatts. And that is your signal-noise ratio. Reason being is that's your signal, that's in a sense your noise or your receiving end, so you actually have 24.77 signal-noise ratio. Now we can determine our total length of the cable now that we have our total loss. So our loss is going to equal your actual total attenuation times your length. Well, we want to find length, and we have our loss. So in this case, we're having a loss of 24.77, and this is decibel milliwatts. Our attenuation is 2 decibels per kilometer, and that's times our length. So what we're going to do is we're going to divide both sides by 2 decibels. And if you divide 24.77 divided by 2, that's easy plug and chug. It's going to give us a length equal to 12.385 kilometers. So that's the approximation of the length of that spool just with these calculations right here. So this is a good starting example. Notice how I'm already converting power to decibels. Well, when it comes to fiber optic communications, that's a very common calculation you have to make. So you're going to have to get used to actually converting everything to decibels. All right, let's go on to the next problem. For our second example here, we're going to touch base on a little bit of the refraction side. Now this one, based on an optical fiber datasheet, the numeric aperture is approximately 0.200 plus or minus 0.015. And we want to determine the maximum angle light can still be propagated when two pieces are spliced together. All right, so we want to actually determine the angle based on this numeric aperture, and we want to determine the maximum angle. And right now it gives us a tolerance. Keep that in mind. On a data sheet, it's not always going to be a solid number. Sometimes they'll give you a tolerance of plus and minus a particular number, and this one did. So first thing we want to do is we want to determine the mid and max values using this actual tolerance here. So if you have 0.200 plus 0.015, and then we're going to do the same thing. We're going to say 0.200 minus 0.015. And that's going to be a simple calculator plug and chug. That's going to give us 0.215 and then 0.185. And that way we can actually check our minimum and our maximum angles. So right here, both of these guys are in A. And we want to actually determine the angle. Well, the way to do that is we're going to use this equation right here. That will tell us our maximum angle. And that's very simple. So we're going to say maximum angle equals inverse sine. Then obviously we're going to put one of these numeric values in here. So we're going to do 0.215. And then we're going to do the same thing on this side. We're going to say our maximum angle is going to equal inverse sine. And it's going to be 0.185. And again, these are simple plug and chug in a calculator. Now for our 0.215, it's going to give us an angle of 12.42 degrees. And for our 0.185, it's going to give us an angle of 10.66 degrees. So which means if you want to determine your maximum angle and still have light propagate between the two splices, your maximum angle you can tolerate is 12.42. However, it's best to actually lean towards this tolerance due to the fact that your manufacturer defect may actually get you closer to the low end of the tolerance. All right, so that was relatively an easy one, but I just want to go over something you'll see on a data sheet. So let's do one last problem. And of course, I saved the best for last. For this one, we want to determine if the link budget will allow an aging allowance of -3 decibels. So we have a fiber optic system here. We have a transmitter. We have a source to fiber loss. This is where your transmitter connects to your fiber. We have about 2 kilometers worth of fiber, a terminal box with a splice in it, and then an additional 3 kilometers of attenuation. And then from the receiving side, we have a fiber to receiver loss. Again, this is where the fiber connects to your receiver module. And then you have your receiver sensitivity of 5 microwatts. So we have a nice little system here, and we want to determine if the budget will allow a little bit of extra loss. So let's go ahead and start inputting some of these. So for the first one, we have 2 milliwatts, and that's for the transmitter. For the source to fiber loss, we have a loss of 4 decibels. So right now, when you connect the fiber straight to the transmitter, you're automatically going to have 4 decibel loss. Then we have attenuation of -2.3 decibels per kilometer, which we'll do the math in a little bit. We have a splice, which is going to be a loss of 0.5 decibels. Again, we have another length here, which is going to be 2.3 decibels per kilometer. And then we have our fiber to receiver loss, which is going to be -2 decibels. And then we have our receiver sensitivity, and that's going to be 5 microwatts. So when you say receiver sensitivity, your receiver is actually trying to pick up dim light. It's actually trying to be sensitive or actually try to detect any light that's being sent down the line. So you're actually putting power in there to detect any light. And that you're actually putting approximately 5 microwatts. So this is not a loss, in a sense, this is a gain. All right, so the first thing I want to do is I want to get rid of these milliwatts and I want to put them into decimal form, because anytime it's in decimal form, it's a very easy system to calculate. So we're going to do the same thing as last time. We're going to say decibel milliwatts equals 10 log and this is going to be your power. We're going to say 2 milliwatts over 1 milliwatt. So it's going to be 10 log over 2 because the milliwatts cancel out, and that's going to give us approximately 3.01 decimals. And I'll tell you what, I'll put that up here, just make it easy on us. 3.01 decibels. All right, we're going to do the same thing for the receiving side, or receiving sensitivity. And again, please forgive my handwriting. For this one, it's going to be 5 microwatts, and it's going to be over 1 milliwatt. And I'm just going to plug and chug that in our calculator, and that's going to give me an answer of negative 23.01 decibel milliwatts. Now the good news is we want to determine our system gain before we move on. So we're going to do this little guy right here. That'll tell us our system gain for our total budget. In other words, when you find your system gain, that's in a sense how much money you have in your account. And your losses is how much you're going to actually subtract out of your account. And hopefully there's money left in your account before all your losses come in. So let's go ahead and determine our system gain, which is our bank account. So our system gain is going to be transmitting power, which in this case is going to be 3.01 decibel milliwatts minus, and this is going to be a minus 23.01 decibel milliwatts. And of course, the negatives cancel out, and that's going to give us a budget of 26.02 decibels. So that right there is what our budget's going to look like. That's how much we have to work with. So I'm going to actually put this to the side up here, our budget. It's going to equal 26.02 decibels. All right, so now let me clean this up so we start see if we can make a budget here. So in a sense, this is our income. Now we need to look at our losses. Well, the first thing I want to do is go ahead and see what our total losses is for our lines, and we want to calculate our attenuation. And that's very easy. It's going to be 2 kilometers times negative 2.3 decibels, because it's a loss, and it's going to be divided by kilometers. So your kilometers are going to cancel out, and it's going to be 2 times negative 2.3. So the loss of that cable is going to be approximately negative 4.6 decibels. So the total loss for this cable, negative 4.6 decibels. All right, let's do the same thing for this cable. So it's going to be 3 kilometers times negative 2.3 decibels divided by kilometers. Those two cancel out. And then it's going to be 3 times negative 2.3. And that's going to give me an answer of negative 6.9 decibels. So this line is going to have a loss of negative 6.9 decibels. Hopefully you can read that. All right, let me clean this up one more time. So this is our gain, 26.02 decibels. Now let's go over our losses. We have a loss of 4 decibels. That right there is our source to fiber loss. Then we have another loss of negative 4.6 decibels, and that's because of the attenuation of the 2 kilometer cable. So we have a loss here, a loss here. Now we have our splice at our terminal box, and that's going to be a negative 0.5 decibels. Apparently they did a pretty good splice. All right. Now after the splice, it's going down the line of 3 kilometers, and that has a loss of negative 6.9. So I'm going to put negative 6.9 decibels. And then from there, you have your fiber to receiver loss, which is going to be 2 decibels. So it's 2 decibel loss. We have all of our losses right here, and then our gain. Well, let's total up all of our losses. We can chug these in a calculator. It's going to give you a grand total of negative 18 decibels. So which means this is your gain minus your loss, or say minus 18 decibels. And that's pretty simple plug and chug in a calculator. It's 26.02 minus 18. And that's going to give us a system gain remaining of 8.02 decibels. So the system gain you're going to have remaining after all these losses is 8 decibels, and it's a positive 8, which is great. It means it's exceeding your budget. In a sense, that's what's left in your bank account. Now the question is, we want to determine will this budget allow for some aging of -3 decibels? So they want to know if we can actually subtract 3 decimals from our budget and still have some remaining left over. Well, if you subtract 3 from 8.02, it's going to be 5.02 decimals, and it's still positive. So our link power budget is still in the positives of 5 decibels. So would this system allow for aging? Yes, it would. It would have an allowed aging of -3 decibels and still have an extra 5 decibels left over. So this is a good system design. Hopefully this is enough practice to get your feet wet. If you have any questions, feel free to let me know, and I hope you all have a good day.